Okay, so welcome to part 2 of the lecture. Now we are just basically continuing to finish off the slides. So now remember we did indicate that, let me just sort of refresh your memory. So we were at this, where we said if we consider variable y and x to be, the drunken head dog, since these variables have a co-movement, meaning they are co-integrated, that's why we then and they're integrated of the same order, and then obviously we would then assume that there should be some long run relationship. So if of course if there will be some deviation, and that deviation is actually what causes a disequilibrium between the two variables. All right, so now then that's why we say if two variables are integrated of the same order, say order 1, so if we have x and y, if they are co-integrated, then obviously we then say there is some linear combination that is stationary. Okay, and that's why we can then say that relationship then is explained by if we have zt is equal to yt minus beta xt. Now where we are saying that this z or this z is a portion of y that are not shared with x, so meaning that that portion is in levels. Okay, not integrated of order 1, but is basically levels. So, and that is basically the equilibrium errors. So we can then rewrite this equation in a regression form where we can now say yt, if we make yt a subset of the formula, will be equal to beta xt plus zt. Now what we are saying here is that this zt will represent a co-integrating vector, and it can be obtained by regressing y on xt. As you can see that here y is a function of xt plus zt. So we are basically saying this zt is the co-integrating vector, which basically then indicates that there is a co-integration, okay, because it has some levels or some portion that are not shared with x, some portion of y that is not shared with x, okay, and that's why it can also be obtained by regressing y on x. Okay, so then we can then say that z, then it represents a portion of y that is not attributable to x, fine. So basically in other words, we can say this z captures the error correction relationship, okay, where y and x are out of equilibrium or disequilibrium, or y and x are in disequilibrium. So in other words, so this z would capture that error correction term, or basically it will then have an error correction mechanism which then capture the degree or the extent to which these two variables are in a disequilibrium. And it is for this reason we can say that z will capture any shock to either y or x, and therefore if these two are co-integrated, then the relationship between the two will adjust accordingly. Okay, so if we take the drunk and her dog, even if there's some, so that z will capture the shock, either a shock either in y, the dog, and x, the drunkard. So if they are co-integrated, then the relationship between the two will still adjust, because if the dog belongs to the drunk, they will still have some co-movement in terms of how they move along, and that's why those two curves are likely to have some co-movement. Okay, so therefore we can now say change in y will be a function of the degree to which the two time series are out of equilibrium in the previous period of zt minus 1. So, and that is why we then say zt minus 1 will be equal to yt minus 1 minus xt minus 1. So in other words, if the value of z is equal to 0, then there is no tendency to change. So meaning that there is equilibrium. In other words, the system is in equilibrium. But if it's different from 0, then there is a deviation from equilibrium or disequilibrium. And that's why we are saying that this z captures the value or the degree to which these two are in disequilibrium, and that's why the z value will not be equal to 2, because it will tell you the degree to which these ones are in disequilibrium. Because if they were in equilibrium, you wouldn't have its value being different from 0. And so for this reason, we then say y, which is a dependent variable, responds negatively to zt minus 1. Okay, because if you make y the subject of the formula, z becomes a negative, and that's why we always then say the error correction term must be negative and statistically significant, because we are saying the pass value of ZTI, which is the error correction term, which is basically capturing the deviation because of the shocks, from the different periods, would then be captured this, and that's why we are saying it must be then negative related, because if we make yt minus 1 as a subject of the formula, then it will respond negatively. So if z is negative, then y is too high and will be adjusted downward in the next period. If z is positive, then y is too low and will be adjusted upward in the next period. So now with the Engle Granger, this is what happens. So what we have actually explained is the whole process of the Engle Granger approach to co-integration, or the so-called residual based approach to co-integration. Then it's actually a two-step, although there are 4 steps involved. The first step is by determining the order of integration of the time series to make sure that they are all integrated of the same order. So meaning you test for unit root. What is unit root? Unit root is basically test whether the variables are stationary or not. Okay, and then the second one is that we have to demonstrate that the time series are co-integrated. So then what we do, once we test for unit root, we estimate the long run equation, and then we create a residual, which I'm going to show you in the e-views. So then what we do is, in order for us to determine whether z is, in order for us, so obviously once we do that, then we have, in order for that to determine whether there's co-integration or not, we have to obtain the co-integrating vector of z. Now what do we do? So we regress y on x, and once we do that, we obtain the residual. Once you obtain the residual, we must then test it for unit root test, and that's why we said it's a residual based approach to co-integration. So once we test that residual for unit root test, so the decision is made as follows. If that residual is stationary in levels, meaning if it's integrated of order 0, then it basically means that there is co-integration. If it's not integrated or if it's not stationary in levels, then it means that there is no co-integration. So in other words, it doesn't mean that if it's not stationary in levels, then you must test it in first difference. No, it must only be stationary in levels, because remember we say that linear combination must be integrated of order 0. So that's the z that we are talking about, the residual that we are talking about. So if it's not stationary in levels, then there's no co-integration. So now once we obtain that residual, then we now finally estimate the error correction model, where we regress change in y on change on x, including this lagged value of the residual. Okay, because we remember that in the previous one we said we are using that zt minus 1, so that's why it must enter the error correction term lagged by 1 period, and you can see here that now here we are no longer regressing y on x, but we are regressing change in y over change in x. Okay, change in y on change in x, t minus 1, and that's why we have that. So, and this basically how the Engle Granger works. Now I'll show you in e-views how all this thing works. Okay, so basically, again, it's just a structure of how the error correction term. So we'll then have change in yt, which is the current value of yt. It's a function of alpha, and then beta change in xt minus 1 minus beta ec, which is the error correction term lagged by 1 period. So this is basically the Engle Granger or the so-called residual approach to co-integration. Then we obviously know that change in y t is equal to beta not change in y xt minus 1 minus beta 1 z t minus 1. So now this beta 0 captures the short-term effect of x on the prior period of y in the current period, whereas beta 1 captures the rate at which the system y adjusts to equilibrium state after the shock. In other words, it captures the speed of error of correction, or it captures the speed of adjustment at which y changes, or y correct itself to equilibrium or adjust to equilibrium, depending on how it was in the past. Okay, if it was depending on how the shock was in the system. And this basically ends now the lecture on the Engle Granger approach.